Hi everyone. In this sequence of mini lectures, we're going to look at some more applications of integration. Those applications share the feature that they're essentially about predicting the future. So we're going to look at situations where when we have some quite general information about how some quantity changes, it might be a population or it might be the amount of chemical that's present in the chemical reaction. We can use that quite general, broad description combined with mathematics, integration in particular, to make some very specific predictions. Okay, so let's see how that goes. So our first round of applications involves what's known as exponential change. So exponential growth or exponential decay. And our first application is to the area of population modeling. In other words, predicting how populations will change over the next few years. Okay, let's look at some figures relating to two countries, to Ireland and to India, a much bigger country. Population of Ireland in 2015, as you see, was 4.65 million. Population of India, much bigger, 1.3 billion, so 1,310 million. Here's a really easy question, not a trick question. The easiest question going to be asked in this course, probably in any other course as well this year. In which country were more people born over the next 5 years? Okay, like I say, it's not a trick question. And hopefully you answered India. Okay, so the figures indeed back that up. In Ireland, the population increased by 290,000 people over that 5-year period from 2015 to 2020. India, on the other hand, the population increased by 70 million. Why is that? Well, the reason is clear. There's far more people in India, more people there to have these children, to have these babies. Okay, so this is pretty obvious, really, okay? But there's actually far-reaching consequences of this. So here's this very general observation that we can make, and now we're going to see some maths really getting to work here and allowing us, on the basis of that very simple observation, to actually make very precise predictions. Because let's look carefully at what that information tells us. Really what we're seeing there by comparing Ireland and India is this very simple but far-reaching observation, which is that the change in the population over this 5-year period, over this period of time, it depends on the size of the population. So the reason that there were 70 million children born in India over this 5-year period is that there was 1.3 billion people there already. And so there was going to be more children born. So what we're seeing there is, to be a little bit more precise about it, is, well, I'm using that delta symbol that we often use to represent change. So this is the change in the population, P for population. The change in the population over that 5-year period. So that, let's say that change in time over which we're measuring this population time, change in time T, and this was 5 years in this case. What we see there is that the change in population divided by the time period is proportional to the size of the population that we started with. Okay, so I've just picked out two data points, if you like, comparing Ireland and India, but we'd see this holding true for any country in comparable circumstances. Okay, so the change in population over the change in time is proportional to the population size that you started with. And again, let's just think back to the case of Ireland and India to see that really that's a very obvious statement. Okay, but like I said, there are far-reaching consequences of this because we can really milk this and get some really precise predictions about what's happening here. Okay, so is proportional to, well, what that means is that the quantity on the left-hand side of that statement, the quantity here, that quantity delta P over delta T, the change in population divided by the change in time, it's proportional to this number P. And what that means mathematically is that that number there is equal to some constant times that number there. So this simple but far-reaching observation already gives us a mathematical looking equation. It gives us this equation that delta P over delta T is equal to K times P for some number K. Okay, let's push that a little bit more. So let's now get into the idea of modeling populations. And by modeling here, what I mean is introducing mathematical quantities that represent those real world quantities. Well, in some sense, I've already done that by referring to P, the population. And we have in mind here, of course, the idea, we have in mind here the idea that the population is changing over time. So I'm thinking of the population as being a function that changes with time. and that's part of the mathematical model. We go a little bit further, and here we're stepping out of the real world and into the mathematical world, but we'll try and keep the mathematical world corresponding as closely as we possibly can to the real world. But one thing we like to do in a situation like this mathematically is to assume that this function p of t changes smoothly with time. So that if we were to draw the graph of the population, maybe increasing because tends to increase, okay, as more babies are born, we'll assume that this is a smooth function, that it's changing continuously with time in that technical sense of being continuous, and also that it's differentiable, so that we'll be able to form the quantity dp dt, the derivative. Where's the assumption there? Where have we stepped away from the real world? Well, where we've stepped away is from the fact that, in fact, a population in Ireland or in India or in any other country always changes by one person at a time. Okay, either through a birth or a death. Populations change not smoothly, but rather discretely. They jump up in steps of one or jump down in steps of one. Okay, but if we're talking about millions of people, a change of one is a tiny little change, and we use this approximation whereby we replace that function that's changing, jumping one at a time, to a function that's changing smoothly. Okay, so we'll just use that assumption and bear in mind, I suppose, in the applications that really we should probably round off to the nearest whole number when we see an answer that tells us the size of a population, because that's what we're going to be doing. Okay, well then we can go back to our observation there that as we saw, we can write mathematically. Oh dear, sorry. We can write our observation mathematically as the statement that delta p over delta t is equal to k times p. And then what we can do is take the limit as delta t tends to 0 of delta p over delta t. And I know what that is. That's the derivative of p. So what am I doing here? I'm saying, well, not what's the change of the population over a 5-year period. We're asking what's the change in the population instantaneously. So we let delta t shrink down to 0. And when we do that, we'll get the derivative dp dt. And then we get this new equation. We get this equation that tells us that the rate of change of population is proportional to the size of the population. So dp dt is equal to some constant number k times p. Okay, so the dp dt, we know the interpretation of that. That's the rate of change of population. Rate of change of whatever the quantity p is, p for population in this case. So here we have the statement that the rate of change of population is proportional to the size of the population, depends on the size of the population. What's this saying? It's saying that the instantaneous, or maybe we could say the daily birth rate in India is going to be much higher than the daily birth rate in Ireland. Okay, kind of obvious statement, but we have this very useful mathematical way of representing that. Okay. Now, in fact, I suppose we could say that what I've done here is introduce something complicated to describe something very simple. Okay, that simple, obvious statement that there's more people born on a daily basis in India than there are in Ireland. But what we've done really is, well, let's not think of it as complicating matters. What we've done here is introduce the powerful technology of calculus to allow us to analyze this situation. Okay. Right, so there's our key there's our key point so far, that we can describe population changes, in this very rough way, by saying that the rate of change of population is equal to k times p. So let's see what we can do with that. Okay. Now, this equation comes about, I think, naturally enough by sort of pulling on the thread of that observation that we made about comparing the populations of Ireland and India. But it gives us actually an entirely new type of equation, one that we haven't really seen before. So an equation like this is called a differential equation. So it involves a quantity p, which is a function of time, and it involves dp dt, which I suppose we might write that as in the prime notation as p prime t. So an equation that connects these two things is called a differential equation. And this is a new sort of a beast for us to deal with. So I'll just say a couple of words about that. Why is this new? Well, previously, everything that we did with differentiation, well, nearly everything that we've done so far with differentiation and in calculus, what we started with a given function. So, you were given a function, maybe y is x times sine of x, and we might have some problem where we need to calculate dy dx, which would be sine x plus x times cos x in this instance. So previously we had situations where we know what the function y is, y equals f of x is, and for some reason or other we need to calculate its derivative. Maybe we're solving a max-min problem or something like that. Okay, so we've seen equations like this one that I've just written down there. We've seen equations that have dy dx in them, but the status of this equation that we're looking at now is very different. What else have we seen? Well, we've seen the problem of integration. We had that problem of trying to find a little f that turns into a given capital F. So if we started with something, let's say, let's take a nice easy one, capital F is equal to x plus 3. Integration is the problem of finding f such that the little f prime is equal to the capital F, x plus 3. So find the little f so that it turns into x plus 3 when you differentiate it. And the answer here, we know how to do this. We have our techniques of integration. The little f that we need here would be x squared over 2 plus 3x plus our constant of integration that we always have to remember. Okay, so again, we've had problems. We've had situations where we have equations that involve derivatives, but here we have something entirely new. What's entirely new about this? Well, here we're given dy dx not as a function of x, so that we just straight up integrate to find the answer, but rather some kind of statement that's telling us how the rate of change dy dx depends on y. Not how it depends on x, which is what we had before, rather how the rate of change depends on y. For example, the rate of change of population, that's how it behaves in terms of the current value of the population P. Okay, so this is a new deal for us. But fortunately, we can use what we know about integration to solve these kind of problems. So in some sense, there aren't any new mathematical techniques that we need to learn here. It's just applying integration in a different setting. Okay, so these kinds of equations, these differential equations, as they're called, they are incredibly useful. So in some sense, most applications of maths in the world today and historically have involved the use of differential equations. Okay, so here's a few examples. Population modeling. When that population corresponds to the presence of a disease, which of course is a virus in the case of COVID, and which is some sort of living organism, more or less, well, we're into the area of epidemiology, trying to predict the spread of diseases. So you'll have heard on the news all about the NFET modeling group chaired by Philip Nolan. This is what they're doing. That's what they do on a daily basis. They solve differential equations to predict the spread of COVID-19. Okay, so we're in that kind of territory. So we can use these differential equations to model populations, how days change, to model the spread of diseases, to predict what the weather will do. So there's differential equations. They're on the news every night because weather forecasting there in Meta and down the road in Glasnevin uses differential equations to predict what the atmosphere is going to be doing tomorrow and next week and so forth. They arise in chemical kinetics. Most of physics involves differential equations. Systems biology involves differential equations, modeling the flow, say, of blood through the heart. They're used in financial forecasting. They're used in modeling human behavior as well. So nearly anything, any system that has moving parts in it, you can probably use differential equations to solve problems about that. Okay, so this is what we call this differential equation, the one that we came across by thinking about populations, the law of exponential change. And this is something that crops up in many, many real world situations. We're going to be we'll be looking at examples of these, and this is our starting point. It comes from that discussion about population, but it crops up in lots of different areas. So this particular differential equation crops up in lots of different areas. Okay, so the next mini lecture, we'll see how to solve this equation and start making those predictions.